Now we'll go ahead and run through examples from Chapter 2. So for problem number 1, we are going to go ahead and just look at Part C. We're told that a study examined waiting times in the X-ray department for a hospital in Jacksonville, Florida. So a clerk recorded the number of patients waiting for service at 9 a.m. on 20 consecutive days and obtained the following results. So we have the number of people waiting and the number of days out of 20 that happened. We want to assign probabilities to the experimental outcome. So we want to know, of these 20 days, how likely was it that 0 people were waiting, 1 person was waiting, 2, 3, and 4. So we can go ahead and we need to know the total number of days, which we do, 20, that's already added up for us, and then we need to look at the number of times it occurred. So the probability that 0 people were waiting is going to be the number of times that occurred, or 2, divided by the total number of days. So 2 divided by 20 is 0.1. Then we'll move on down to 1 person waiting. That happened on 5 of the 20 days. So 5 divided by 20 gives us a probability of 0.25. Moving right on down the row, 2 people waiting. We had that happen 6 times, so 6 divided by 20 total days gives us a probability of 0.3, or you could say 30%. Then the number of people, we had 3 people waiting 4 of the 20 days for a probability of 20%, or 0.2. And then 4 people were waiting on 3 of the 20 days, or probability of 0.15. Now what you want to make sure you do before you just automatically assume this is all correct is you should add up the probabilities that you've found, and you need to make sure that they equal 1. So if we added all 5 of these probabilities up, we would see that our total is 1. Probability is always a value between 0 and 1. It's never negative, and if you add them all up, or all the probabilities in your event, it needs to total 1. Now let's take a look at number 6. Number 6, we have a sample of 100 customers of Montana Gas and Electric, and this is in regards to their monthly bill. So 13 people paid an amount between $0 and $49, 22 people paid between $50 and $99, and so forth. Part A says let A be the event that monthly charges are $150 or more. We want to find the probability of A. So we want to find the probability that of these 100 people, they are going to be paying more than $150. So the first thing we need to do is look at our table and figure out how many people paid more than $150. So 26 people paid between $150 and $199, and 5 paid between $200 and $249. So 26 plus 5 gives us 31 people. Those 31 people paid more than $150. Now, in order to get the probability, similar to number 1 that we just did, we need to divide the number of people that we had, the number of times this happened, number of occurrences, divided by the total number. So 31 divided by 100 gives us 0.31. Okay. So let's look at part B. Let B be the event that monthly charges are less than $150. Find the probability of B. So the probability that these people paid less than. So less than $150 is going to be the 13 plus 22 plus 34. Or we could look at that another way. We already know that 31 people paid more than $150. So the complement of that would be 100 people that we started with minus the 31 that paid more. 100 minus 31 gives us 69 people who paid less than $150. But again, to get the probability, we need to divide that by the number of people that were surveyed, or the number of people that they collected data on, and we can see that 0.69 is our probability here. Now again, if we looked at this, 0.31 plus 0.69 gives us a total probability of 1. Moving on to number 7, it says, suppose that a sample space has 5 equally likely experimental outcomes. Equally likely, that means they have the same probability of occurring. So we are calling those different outcomes, or the whole sample space is made up of 5 sample points. So each sample point, E1, E2, E3, E4, E5, they all have the same probability. That probability has to total 1, so 1 divided by 5 gives us a probability of each of them, or for each of them, of 0.2. So 1.00 divided by 5, they each have a probability of 0.2. So event A, is made up of event 1 and event 2, or outcome E1, outcome E2. Event B is the set E3, E4, so outcome 3, outcome 4, and C is the event outcome 2, outcome 3, and outcome 5. We want to first find the probability of event A. So what's the probability that we ended up with our outcome 1 and outcome 2? So what we need to do is we need to add up the probabilities for each of them. So the probability of E1 plus the probability of E2. We said that each of these had a probability of 0.2. So the probability of E1 is 0.2 plus the probability of E2 is 0.2. Total probability of A is 0.4. Then move on to the probability of B. So again, we will add up the probability of each individual outcome, or the probability of outcome 3 and outcome 4. Again, we have 0.2 plus 0.2 for a probability of 0.4. Now we need to look at event C, probability of C. So we have the probability of outcome 2 plus the probability of outcome 3 plus the probability of outcome 5, or 0.2 plus 0.2 plus 0.2, for a total probability of event C being 0.6. Okay. So part B asks us to find the probability of the union of A and B, and then we want to know if A and B are mutually exclusive. So remember, union means that it includes every element in each set. So everything that you see in either A or B has to be represented in the union. So A has outcome 1, outcome 2. B has outcome 3, outcome 4. So our union, A union B, needs to have all 4 of those. Outcome 1, outcome 2, 3, and 4. We want to know the probability of that, so we would need, again, to add up the probability of all 4 of those. We know each of them has a probability of 0.2, and there are 4 outcomes in our union, so the probability there is 0.8. Now the second part of this question, it asks, are A and B mutually exclusive? Mutually exclusive means nothing in common. Sometimes you may hear this said as the sets are disjoint, nothing in common. So we want to look at the intersection. The intersection is what they have in common. And it is denoted kind of with the ups, or with the N looking symbol. Union somewhat looks like a U. Intersection somewhat looks like an N. So if we look at A and then look at B, they don't have anything in common. So since they don't have anything in common, they are mutually exclusive. Yes, mutually exclusive. Part C of this question asks us to find the probability of B union C. So again, we want to look at the union of B and C. What do we include in our union? needs to include everything that we see in B and C. Now what's important to pay attention with this one, you don't double up on things. For instance, we see outcome 3 in both B and C, but we only include outcome 3 once. It's not going to happen twice in the union. So we have outcome 2, outcome 3, outcome 4, and outcome 5. Again, we want to know the probability of B union C. So we want to add up the individual probabilities. Again, we know they each have an individual probability of 0.2. There are 4 of them, so our probability of B union C is again 0.8. Now, if I asked if these were mutually exclusive, they would not be, because they share the element or the outcome 3. Now let's take a look at problem number 12 from chapter 2. We have 2 events, A and B. We are told that the probability of A is 0.5, the probability of B is 0.6, and the probability of the intersection of A and B is 0.4. So we want to find the probability of A given B, and then we're going to find the probability of B given A. So we have to think back on some equations here. This is the conditional probability equation. So if you need to, you can flip back in your notes there. Dealing with conditional probability, we know that the probability of A, given that B happened, is the probability of the intersection of A and B divided by the probability of B. Given that the probability of B is not 0, which we're told it's 0.6, so it's not 0. So now we need to go ahead and plug into our equation. So we're told that the probability of the intersection is 0.4, and the probability of just B is 0.6. So 0.4 divided by 0.6 is 0.667. So the probability of A, given that B happened, is 0.667. So now we need to look at it the other way. We want to find the probability of B given A. So things change ever so slightly. But our equation now becomes the intersection of A and B, the probability of their intersection, now divided by the probability of A. Sometimes it's tricky to remember which one goes in your denominator. Just look at the one that's listed second. A is second, so A is going to go below the line in our denominator. So our numerator is the probability of the intersection, 0.40, divided by the probability of just A, which is 0.5. 0.4 divided by 0.5, we have a probability of 0.8. Another thing you want to take a look at, make sure that you fully understand, is the multiplication law. There's a newspaper example in our notes that covers that very well. It's very similar to the equation we used here, but in the multiplication law, we've got one side of the equation, I'll jot it down here, multiplication law, the one side of the equation is the intersection, and the other side is our conditional times our probability. So it would be P, B given A, times the probability of A. Okay, so just take a peek back at that in your notes. Make sure that you grasp that concept, and you should be good to go. Just let me know if you guys have any questions.